हम्म, ठीक है। क्लास स्टार्ट हो रही। Hello everyone. So today we are dealing with week 12 and then we will solve some of the problems. So a gentle reminder that I am also taking an extra live session on 17th of April, I guess. 17th. Yeah, 17th of April from 6 to 7. Okay. So in that we will just revise the concepts like with the quick short revision and then we will see some of the problems also. So today we will be seeing this week 12. So week 12 is basically towards more of a formula based questions. It will be having some formula based questions. But what I have observed in NPTEL, so you will have most of the questions from week 1 to week 10. Okay. So you please do these weeks very well because from these most of the 80% or 90% questions will be coming. 90% in fact. So the remaining 10% will come from week 11 and 12. So yeah, moving ahead. Yeah. So in the last class we saw some of the problems related to week 11, and if you
Excuse me.
remember,
Excuse me.
we also saw this Markov chain and page rank algorithms. Yeah, sure, sure. You can
Yeah,
speak.
excuse me. How many questions are set usually in the
Uh,
final exam?
yeah, it depends on the paper pattern, but last time it was 60, I guess.
60.
Uh, Last
For
time I
three
gave
hours.
applied, yeah, 3 hours it will be. So I also gave some of the NPTEL exams, so you will basically finish in less than 1.5 hours because these type of problems will be not very much tough. So especially this subject, if I'm telling. It will be more on the concepts that is continuously repeating. For example, least square, least norm solutions, and then there will be consistent, non-consistent. Sensitivity analysis is one of the main topic. Sir will definitely give some questions from this. Uh, at least 5 questions will be there, and singular value decompositions. These things will be there.
Okay, thank you.
Yeah. So what is the exam date? When is the exam?
28th.
28. Is a hall ticket released?
No, I don't think so.
Yeah, so from the other exam, it is released. Those who are scheduled on 20th, they are released. But 28th and 29th is yet to release, I guess. Yeah. So in while finding the solution for ax is equals to b, which was our main prime importance, or for this particular thing only we did lu qr decomposition because this implies x is equals to a inverse b. A inverse b. So that was the case, and a inverse, calculating the a inverse for higher order is tough. So for that we with these things. Okay. Now, we also saw some of the properties. If A is rectangular in the sense it is not square. So in that case, we're having two conditions: least square and least norm. So, what were the condition for least square? Least square means it will be tall, and least norm it will be wide. Okay. So one of the main thing to remember this is like in the wide matrices. So you are having um, number of unknowns as more than number of equations. So for that you need to have some of the assumptions. So you will have so many solutions. So what solution will be the best one? So in that what solution will be best? The solution which is having the least norm. Okay. So for that we used to find a particular solution. So in wide matrices or this least norm solutions, you always have a solution. Okay, you always have a solution. But in this case, least square, it means a tall matrices. You may or may not have solution. So that was the case, and that's why you calculated the approximation error. And in that case, when there is no solution, then you find the approximated solution. In that case, error you try to minimize the error. Okay, so least square. This was a least square. I hope this is remember. हाँ, so यहाँ पे बंद हो गया क्या? So yeah, I don't know what clicked on my system, so it went to sleep. So yeah, so basically, then we also saw how can we write in terms of singular value decomposition. So singular value decomposition is meant for all type of matrices, irrespective whether they are square or not. Whereas eigenvalue decomposition is only meant for square matrices. Okay, why that was important? Because that helps us to see it in a spectral form. Okay, so now uh, we have seen the solutions and all, but have you ever observed like sparsity of the solution also matters? So what is a sparsity? Sparsity means there will be so much sparse, means there will be so much zero but the information is less. So in that case, the number of non-zero elements of any vector is called a zero norm, but actually it is not a zero norm. So basically norm is defined from 1 to up to a finite number. Infinity norm is also defined, but zero norm is not defined. But basically for just checking the number of non-zero entries, we call it as a zero norm, but it is actually not a norm. Okay, but it is called as a zero norm. Or also it doesn't follow the properties of basically a norm, so that's why it is not a norm. Okay, but it is represented in that form, so it doesn't follow this property. Okay, now we also want that we want the number of entries to be maximum, means we want this. Okay, because we don't want the sparse solution, we want the solution to be efficient. Okay, so in that case, okay, sorry, minimum. Okay. So basically, the objective is to compute a solution Ax is equal to b such that this is also minimum. Okay. So, because non-zero entries should be minimum. Why it is minimum? Because if you try to calculate the inverse of a matrix where it is having so many zeros, okay, whereas some only one or two, three non-zero elements. So in that case, the calculation is easy. Okay. So you have a set Rs, Ax for x belongs to R power n, such that this is less than or equals to some other set. Okay, but this is not a subspace, you remember. So subspace has what two properties you always remember? Close under scalar multiplication and vector additions. Okay, so given any b belongs to Rs, compute x such that it is minimum or and it also follows Ax is equals to b. Okay, so example, consider A belongs to M cross N where M is less than N. So what will be the case for M is less than N? Wide or tall? It will be wide. Okay, and we assume that A has linearly independent rows. So Ax is equals to B, where AM can be written in terms of these rows A11, AI1, AI2 to AIM, where it is belongs to R M cross M. So you will have these if you can write like this, so Z is equals to AM inverse B. Okay. So you need to make sure. So one of the way is free not linear spines. So what is that? So you can approximate any function using other functions. So if fx it can be approximated as terms of f cap of x, which is equals to alpha 1 fn of x, alpha 2 f2 of x, so on alpha n fn of x. Okay. So this, if it is y observed and this is a function that you have approximated, you can write like this. And also m is greater than n. So in that case, A is equals to, suppose, what happens? Any function can be represented in terms of matrix as matrix, as we have also observed, because matrix is nothing but uh, mapping. So you will have this one, and this is F. So F can be represented as A. Okay, so A can be written as a Fk of xi, where x is the input and y is the output. Okay, so we want this. Okay, because anyway, whatever the observation you are getting, this is alpha x minus, or what is the true value. We want this. So one of the approximation is ReLU. So ReLU is one of the function which is f, okay, which is having this property. If x is less than or equals to a, then it is 0. If it is greater than, then it will be x minus a. So a can be 0 here. So is 0 and x. Okay, where a can be anything. So it can be represented as 0 and x minus a. So it should not be like this. A should be like this. Okay, so this is one of the approximation. Like, how can you approximate for x? So this is y, okay, such that it is 0 for x less than or equals to a, and x minus a for x greater than or equals to a. Okay, so if you can write uh, every observation of x in terms of this function y, so you can, one of the approximation is ReLU function. There are many of other approximations, which is tan h, and then exponential, and these sigmoid. So these approximation by sir has used, because these approximation are used in neural network. So in neural network, what you have input x, okay, and then you are passing it to other layer. So it is one layer, layer 1, layer 2, okay, and every node is connected to like this. Okay, now you always pass it to a function where y, okay, so y is another pass to a y dash. So y dash, okay, so these are some input parameters as a input features. Okay, these are some hidden layers, neural network hidden layers. So these y is actually approximated as y dash is equals to f of y, where y is equals to wx plus t b. So w is actually weight associated with every connection, and this b is actually the bias. Okay, now this observation is also not sufficient for logistic regression. So you pass it to a ReLU function or sigmoid function. Sigmoid function, if I remember, this is f e of x plus e of minus x, e of x minus e of minus x. This is sigmoid function. This is having some properties. What properties? It is truncating every less than equals to particular value to 0, and for every other value, it is keeping the same value. So this is one of the thing. Okay, so knots is actually the location of the corners of the spine. So what are the knots? These are knots. Okay, and so also assumptions are equally spaced. So suppose f on 0 to 1 and tolerance is equals to this eta is given. Then find f cap based on the knot equation. So what is knot? You want that this p of n, which is a sequence where 0 less than 0 greater than x1 to x2 to xn is less than 1. So all these values are equally spaced between 0 to 1. So you with minimum number such that this approximation should be less than this some value. This is some value, some tolerance, which is basically less than equal, very much less than 1. So it will be around 0.01 or something. So you want this, okay? F is given, you want f cap such that this follows, and you also have not. Okay, so how will you do that? So if you write p n of k, so this is also for every suppose this is star, sorry, so p n of star, this is 0 to x1 greater than x1 greater than x2, all is less than 1. So this is, you have these equally spaced x0 x1 2xn. So suppose f cap you write like this. This is summation of k is equals to 0 to n, uh, where alpha of k x minus k upon n plus 1. This is, suppose this is f of k. So you want this alpha of 0. So uh, this is the number of non-zero entries. So what happens if you have so many entries of this one? So the computation will be increasing. Okay, so you want this particular thing to be as less as possible, and now you're doing the approximation. Okay, so in that case, sir gave the essence of where this zero norm is used, or this sparsity is used. Sparsity vector is, it is also called sparse vector. So in that you want this as much as possible. This is a number of non-zero entries. Okay, so you want minimizing alpha mod of alpha 0 such that this is less than equals to this is eta, this is called epsilon. Sorry, this is epsilon. Oh yeah, epsilon for all x belongs to 0 to 1. When x belongs to 0 to 1, knots were given. Okay, so if we have observed yj is equals to f of x j for j belongs to 1 to m. So you want this. Okay, so, a is what? A is nothing but xi minus k divided by n plus 1, where plus means it will be same value for greater than 0, otherwise it will be 0 for others value. Okay, so these are some observation values, because m cross n was the unit of the matrix, dimension of the matrix. If I, yeah, this is only the thing. So you have, yeah, so if k is these many k's are there, so you will have these many number linear function, which is also called basis functions. So you want this to be minimum such that, as I told, every function can be written in terms of matrix. So this a alpha minus y mod of 2 less than equals to, this is epsilon. So how will you do that? So one of the way is to do using one norm. So what is the difference between one norm and the two norm? What is the difference between one norm and two norm? Anyone? So yeah, we will see here, because as I in one of the exercise I told, please try to plot every norm. So this is two norm. I'll plot it. Seeing and observing is very important in linear algebra. As we know, this is two norm. Okay, this is one norm. This is infinity norm. So this is infinity. Then this is one norm, and this is two norm. So if you see the graph of these two equations, so you can see here you will have edge in one norm, whereas in two norm you don't have edge. So what does it mean? It is having a particular sparse. So this one norm ensures sparsity, whereas it doesn't have edge. Okay, it doesn't have edge, so it is creating the continuity. So wait, we will see here also. So this can also be written using one norm. So if we minimize where a alpha belongs to r n plus 1, minimize this one norm, and such that this a alpha minus y mod of this is less than equals to epsilon. So how can we write this? And uh, if you see one of the property, this if eta is 0, suppose epsilon is 0, so alpha is equals to y. So one norm, as we know, this is this particular function. Okay, so where alpha is equals to this particular vector. Okay, so if you plot this is one norm. Okay, and if you have solution alpha, so this is one of the solution alpha. If you have solution alpha 1, so this is one alpha 2, this is alpha 2, alpha 3. wherever this corner is touching. Whereas in this case, you will have this as an alpha plane. Okay, in 2 norm. So what is the difference between 1 norm and 2 norm here? Can anyone tell me? How many of you have uh, watched this lecture? Okay. Ananda, would you like to tell?
Ma'am,
Yeah, yeah.
can you repeat the question?
What is the difference between 1 norm and 2 norm? Not through formula, through graphically. How can you differentiate between 1 norm and 2 norm?
One norm is it is given in the figure.
Yeah,
It is
true,
a
true.
diamond-like
Yeah,
structure.
yeah, true. So, what it interprets? Very true that you can see from the figure. But what it is interpreting? So, what it is interpreting, first of all, when you're passing through this norm structure, so then you are definitely have to pass it through one corner. Whereas in this case, the corner doesn't exist. Okay, you have to pass it to any value through this, like this. But in this, you have to pass it to one of the corner value. So when we choose in typical setting, the L2 norm is always better than, I'm telling, because this is one of the main thing that we need to know. Okay, so in typical setting, L2 norm is better at minimizing the prediction error as we saw earlier. Okay, in case of tall matrix, that was nothing but least square. Yeah, and if we remember, this was the first solution of A transpose A inverse A transpose into Y. This was the X. Hmm? But we do find L1 norm which is used sometimes despite of L2 norm, which is outperforming in almost every task in minimizing the error, because this L2 norm is a square and that is also equivalent to MSE, mean square error. Okay, that's why mean square error is always used everywhere used, and that is a equivalent form of L2 norm. And this is primarily because L1 norm is capable of producing a sparser solution. So do you remember this is a sparser solution? How I'm telling you. So to understand why an L1 norm produces a sparser solution over L2 norm, during regularization we need to visualize the space. So as we can see this particular space, this space and this space. So in this image, we can see the solution for the L1 norm to get to the line from the inside our diamond space. This is a diamond. Okay. It is best to maximize x1. So if this is x1, if this is x1 and this is x2, and this is norm of xl1. This is norm of x2. Okay. So it is in order to reduce. So in order to get to the line from inside our diamond space, it is always best to maximize this x1, not x2. We are not using this x2 as all. So instead of two variables, we are using only one. So instead, what is sparsity? Sparsity means less number of entries, non-zero entries, less number of non-zero entries. So if you want to maximize it, you will try to maximize x1. You will not use x2 because this is passing through only x1. And if it is passing through this x2 also, then it will not pass through x1. So in that case, you will always maximize x2, not x1. So it is what is saying, it is best to maximize x1 in the first line, whereas and leave x2 as 0. So x1 this is maximizing, it is same as maximize x1 and x2 is as 0. Okay. Whereas solution for L2 norm, as we can see from the second graph, to get to the line from inside our circular space, to get to the line from inside our circular space, it will be the combination of both x1 and x2. Okay, so it is likely that the fit for L2 will be more precise. However, the L1 norm, our solution will be more sparse. So I agree that in this case, x1 and x2 will be both involved. But to ensure the sparsity, you have to use L1. Okay, as we can see from the graph itself. So L1 norm ensures the sparsity, as we can see from the figure. So since also you remember, since L2 norm, what we can say word penalizes larger errors more strongly because this is giving you MSE. It will give solution which has fewer large residual values, whereas L1 norm, on the other hand, it will give solution with the large residuals. It will give solution with, because that will not minimize that error. Residual means error, but it will also have lots of zero in the solutions. Okay, so L1 will have the lots of zero in the solution, that is giving the sparsity. Hence, we might not use L1 and L2 at the same time. So that we will see in a seconds. So I hope this is clear. And also I would like to give one of the real life example. So since we might want to use L1 norm when we have constraint on the feature extraction, means we want the feature to be less number of features. Okay, so then in that case we want some of the features only to consider or some of the other not features. Like if we use L2, so all the features will be included, and we don't want that. Okay, so we can easily avoid computing large number of computationally expensive features at the cost of some of the accuracy. Okay, so in that case L1, since L1 will be giving solution which has weights for larger number of features set to 0, so in that case we can use. So our typical case would be a real-time detection or tracking of an object in AI/ML case, using a set of diverse, suppose handcrafted features. If we see support vector machine, so in that case you used L1 now. Okay, so I hope this is clear. Yeah. That's why it is written in terms of L1. And in the future, you will see in practice we use both. We use both. Okay, so if A belongs to M cross N given, and you can write using singular value decomposition. This is, as we know, this is the rank 1 matrix, rank 1 matrix, rank 1 matrix, and this is singular value decomposition of A to compute the nearest rank. Okay, so I think this is something is skipped or what? Okay, so yeah, in order to produce sparse solution, you have to minimize the element norm. That is, I think from the figure it is clear. And yeah, So moving to the rank approximations. Okay, so if it is given, we can write using trigonometric decomposition to compute the nearest rank, which is a k minus 1 matrix. Okay, the nearest rank. So you can write in terms of B. So B is another matrix where you have to consider only k minus 1 vectors. Okay, so B is another matrix, we have to consider only k minus 1 vectors. So it is actually, and also why it is like this, because since the singular values are decreasing in number, it is arranged in terms of decreasing order. So it is actually the approximation. So the matrix with the structure symmetric top list sparse matrix. So actually this is a nearest rank. This is a k rank k minus 1 matrix. Okay, so you have to only consider this. Okay, so actually there are so many questions based on this particular formula in week 12. We will see that. Okay, you remember this formula. So yeah, if R n cross n is a vector space over capital R, so this is also a subspace of R n cross n. Uh, then if you are given a time series data, suppose yt is given for different time intervals. So what is time series data? Means at time t is equals to 0, time t is equals to 1, time t is equals to n minus 1, you will have the data associated with it. What can be the data associated like time series? The weather forecasting or like that. We always use time series. Okay. So in that it is autoregressive. So what does this mean? Autoregressive means that sometimes it is repeating. Okay, so y1, y2, y3, y4, y5, it is observation of time series data to n. So if you can write like y4 based on y1, y2, y3, and y5 also as based on these data, like you are predicting the other the future time series data based on the previous one. So how will you predict? Okay, so in that we are associating the weights. It is alpha 1, alpha 2, alpha 3. So always remember this alpha 1, alpha 2, alpha 3 is actually the same for predicting either y4 or either predicted y5 or either predicted y6. So this property is also called autoregressive property. This is actually seen in time series analysis. So yeah, if you can write like matrix like A tilde, where this is y1, y2, you can definitely write like this. I hope you can write. This is y1 tilde, y2, y3, y4, y2. Then your circulating is y2, y3, y4. You can write like this. And if you multiply this alpha 1, alpha 2, alpha 3, so this is also called Topliss matrix or hanged matrix. Okay, I think this is not called Topliss matrix. Topliss matrix is the diagonal elements are same. In this case, diagonal elements are not same, but yeah, it is circular in this case. This y2 is coming here, and y3 is coming here, y4 is coming here, then y5. Okay, this is actually not a neither total is not a circular. Circular means if this is a row, then it will be circulating it as like this in the second column. This is circulating like this in third row, like this. But this is called the hanged matrix. Okay, so suppose it is A clean. This is called hanged matrix. You remember. So, we want to approximate to some lower rank. This is low rank of approximation will not have hanged structure. So, low rank approximation will not have hanged structure. So, here we are not seeing this hanged structure in this low rank approximation. I forgot what sir used to say here. But yeah, so if this omega, big omega, be a subspace of R m cross n. So this can be a matrix A where m is n. So the subspace will be symmetric matrices, and this is actually the space of hanged matrix. So hanged matrix, you remember, you are shifting this everything, and you are just adding everything. So what will the next one? It will be y6 tilde. Sorry, this will be y5 tilde. This is y6 tilde, y7 tilde, y8 tilde. So here you can see this y6 is common, y7 is common. But yeah, this is adding. So this is actually the hang structure. Okay, so if A is belongs to this m cross n given to us, compute the nearest rank deficient matrix in symmetric matrix to A. So how will you calculate? We have to see up to what sigma value we have to consider in calculating the nearest rank matrix. So if A be a suppose rank K matrix, so average we need to minimize it with respect to nearest structure low rank approximation. So this is also called structured low rank approximation of A. You want it to be in a particular structure. Okay. So this rank of X should be less than or equals to K minus 1. Then only you can subtract it. Okay. And X should be belongs to this big omega, because big omega is actually the subspace of A. Okay. So given A belongs to M cross N, and this big omega belongs to R M cross N. This rank of A is also K. That is also this omega is actually the subspace of R M cross N. When M is equals to N, then this omega is actually the symmetric matrix. So Hank matrix and Topliss matrix. So Topliss matrix will be same. So you want to optimize for the nearest structured low rank approximation. We don't want particular matrix to be a particular rank. We also want it to be a particular structure. So that's why we are keeping this as a constraints. Okay. And this is actually low rank constraint. This rank of X less than or equals to X minus 1. So for symmetric matrices, we know this uh, A belongs to R n cross n, and we know this is nothing but eigenvalue decomposition. What was that? V, I think V, yeah, this was like this. V inverse. And V inverse equals to V transpose in case of orthogonal matrix. Symmetric matrices. So this is V transpose, and like this will be written. Okay. So and if you want to approximate with respect to K minus 1, you have to take the K up to K terms. Okay. K sigma values. So nearest K minus 1, this is a K rank approximation. So because this is rank of A is K. So the nearest rank K minus 1 matrix is actually this particular matrix. Okay. Yeah, but this is also symmetric. So given any matrix, and this is this one, so B can be written like this plus, and if you add this one, so alternating between structure constraint and low rank constraint. This is also confusing to me. Represent all matrices of size M cross N. Set of all matrices with rank less than or equals to K minus 1. Okay. So this is A, and set of all, suppose if this is A matrix, okay, and you are defining this as subspace of structured matrices. So in that subspace you have to select one. Okay. So that's why this was the objective function X minus A. Okay, because X belongs to structured set, and the rank of X should be less than or equals to K minus 1. This is a low rank approximation. Should be less than or equals to K minus 1 because this rank A is K only, and the Frobenius norm. Okay, Frobenius norm should be nearest structured low rank approximation of A. So this is the actually constraint here. Okay, if we see this visually, okay, so we have to find the intersection. Okay, suppose this is a set with a structured matrices, and this is a set of the matrices with rank K minus 1. This was a low rank approximation, this green color, and this one was a structured approximation. And if we find it properly with the intersection one, so this will be the set of all structured matrices with rank K minus 1. Now also you have to equate it with respect to nearest structured low rank approximation. Structured low rank approximation, SLRA. Okay, it represents all matrices of size M cross N. Okay, now let us see the Hank structure. So if omega is actually the linear space of all the Hank matrices of M cross N, The solution, if you want to see particularly, we have to see with example. But yeah, how to do this, sir has told. But I think from this, there will not be question to solve it. But if there is a particular formula, like closed form equation for solving any formula, for example, this one. You have to find k minus 1 rank approximation vector. So you'll have to use this particular formula. But other than that, conceptually, uh, you don't need to remember everything, but try to understand. Okay, try to understand and go ahead. Okay, so this is one of the understanding thing. I hope if it is not clear, you can watch the lecture also. But yeah, I tried to explain whatever I understood. Now, if you see the hang structure, this big omega is actually the linear space of all the hang matrices of size m cross n. So you know this is a B, which is a projection on this particular big omega. So this can also be called as a B tilde. So B tilde, if you write like this, B11, and if you sum B11 plus B12 divided by 2, if you sum B11 plus B12 plus B13 divided by 3, this will be full rank matrix. So in order to, by doing this, you will be getting the full rank matrices. And if you do the SVD, okay, so if big omega belongs to R, M cross N be a subspace of structured matrices, as we know, and B is also this one. So B will be nothing. Every matrix in this particular thing will be written as B11, B12, B13, and so on. Which will be the ordered basis of this particular big omega. So there will be for all y belongs to big omega such that y is actually the sum of all bi. So this is falling from the property of linear independence. So I hope this is clear. I don't because in what was the case in our case in previously what was the case for linear independence, if there are so many vectors, suppose v1 v2 v2 to vn, so the linear combination of all the vectors will be summation of alpha v. So if there are v1 v2 vn are vectors, okay, this will be above vectors will be linearly independent. Li if there exists alpha 1 to alpha n such that there exists such that alpha 1 v1 plus alpha 2 v2 so on alpha n vn a linear combination of vectors. Let's say is y, and if y is 0, if and only if alpha I will be 0. Okay, so if and this v1 v2 to vn will be also called basis because these are the linearly independent. This can also be called the basis for particular subspace. So in that case also we are calling it v1 v2 vn or all matrices. So same can be the same can be interpreted in terms of matrices also. So if this is a set and there is existing this one, so this will be the basis matrices. So given this x belongs to this capital omega and the rank of x is equals to k, which is less than or equals to m of n, as we know, whichever is minimum, it will be m on n, which is a number of rows and number of columns. So we have to find y belongs to this capital omega such that the rank of y should be less than k. And if we go to the formula, the actual problem that we had, this is the minimum of this x minus y for Frobenius norm, which should be equals to the closest singular closest structured low rank approximation. So where x is can be also written in terms of this linear combination of the basis matrices. It is a bi. So this bi is a these matrices that should be linearly independent. So this capital omega is actually the symmetric matrices and B is actually B1, B2, Bn. All other linearly independent matrices. Okay, so linearly independent matrices, the same analogy will be following from this particular thing that whatever written in blue color. Okay, so in order to do this, we have to formulate like this. X, I hope this I'll not get into it. what is the actual okay, so that's it. I think actual closed form equation is not written. Yeah, this is written like this, I guess. But how it is formulated, you please try to remember this. Uh, yeah. So this is the formulation. We have to minimize with respect to y and b. Now, now we are minimizing with respect to y and b. And you remember this, what is C of bi? So C of bi, xi minus yi square subject to this particular thing. Or we can also write v transpose v is equals to 1. So you can see into it. This is the outer optimization. This is also can be written as an inner optimization. We have to go into very depth. Like, I don't remember, I watched the video 1 week back only. But yeah, at that time I remember yeah, C of B1 is 1, C of B4, this is B4, C of B6, C of B2, B3, B5 is equals to 2, B2, B3, B5, 1, yeah, so number of 1 in this element. So C of B1 is it's giving number of 1, 1, 1, and this is also 1. But in case of B2 there are 2, 1, B3 there are 2, 2, 1, B5 there are 2, 1. So that's why it is 2. Now you, as we can see, we can write in terms of a basis vectors, and y also in terms of basis vector, because those two x and y belongs to big omega. Okay, now we want to minimize the sparsity also. Okay, so the number of ones should be less. So C of bi, uh, xi minus yi whole square. So this should be same for all the summation. Okay, that's why it's summation. And subject to this particular y should also be 0. So this can also be written like this, summation of y and bi such that v transpose v is equals to 1. Okay, the other thing is outer optimization. This can be written in terms of matrices. So this is one of the case. Okay, so this lecture was little more depthy. I hope you should remember this. What is a Hank matrix? Then uh, what are the things that you can remember for this week? I'm just telling. Yeah, please try to understand the difference between the L1 and L2 norm, and what is L0 norm, and how in order to minimize the number of entities you are using L1 norm. And it basically we also use like regularization. So in case of regularization, uh, which regularization we should use, L1 and L2. So this was the L1 and L2, and then what are the hand structure, time series data. Okay, let's see the questions. Okay, so this is the question number 1. If A is belongs to R 4 cross 4 such that A is actually this thing, where sigma I is actually the highest singular value, while VI is actually orthogonal column vectors in SVD of A. Now find the nearest matrix to A in the Frobenius norm with a rank of 2 given. How will you do that?
Can the question be enlarged a bit?
Yeah, sure.
Thanks.
Yeah. Do you remember the formula that we saw?
Sigma 1 U1 V1 transpose. That one.
Yes. Plus.
Plus sigma 2 U2 V2 transpose. Plus sigma 3 U3 V3 transpose.
Okay. With the
I
rank
want
2.
only rank 2, so first two will be good enough.
Yeah, why sigma 3? You don't need to use sigma 3 in that case because rank 2 is given. And Frobenius norm is nothing but the norm you want to minimize for the matrix. Norm that you wanted you used to minimize in for the vectors was L2 norm. Where similarly for matrices it is Frobenius norm. Okay, so it will be definitely we will see the solution also then. Sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose. Then sigma 1 is nothing but 3. U1 is, let's solve it in a big space. This is a space. Sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose. Okay, so sigma 1 is 3. U1 is minus 1 by root 2. 0, 0, minus 1 by root 2. V1 transpose is nothing but minus 1 by root 2, 0, 0, minus 1 by root 2, plus sigma 2, which is 2, and 1 by root 2, 0, 0, minus 1 by root 2. V2 is 1 by root 2, 0, 0, minus 1 by root 2. This is 4 cross 1, this is 1 cross 4, this would be 4 cross 4. Now, can anyone tell me the entries? 4 cross 4. 1 by 2,
0, 0, 1.
0, 0, 1 by 2. 0, 0, 0, 0, 0, 0, 0, 0. This is 1 by 2. This is 0, 0, 1 by 2. This is 1 by 2, 0, 0, minus 1 by 2. 0, 0, 0, 0, 0, 0, 0, 0, minus 1 by 2, 0, 0, 1 by 2. And if we sum it, 1 by 6, 1 by 6, 1 by 6, 1 by 6. Oh,
It's 3,
so sorry. Yeah. It will be 3
3
will
by 2.
be, yes. So this 3 by 2. This is 3 by 2, this is 3 by 2, this is 3 by 2. Now this is all will be 1 or minus 1. 1, minus 1, minus 1, and this is 1. So let us do this. This is 1.5 plus 1, 2.5, because it is written term in that term. So 2.5, this is 0, 0. This is, it should be 1.5, this is 0.5. 0, 0, 0, 0, 0, 0, 0, 0. Yeah, before clicking on any answer in the exam, you please solve it one by one. Because what happens if you do any mistake, your marks will be lost, irrespective of the fact whether you know the concept or not. Okay,
Exam will be
this
allowed
is
to scribble. I mean, there will be pen and paper for us to scribble such.
yeah, they give pen and paper.
As the present assignment 12, question number 3, the two options are printed to be same. I have pointed that out, but there's no response to now.
Yeah, then in that case,
1 and 3 are both the same thing printed, and one of them has to be changed. I mean, that will be answered. Right. If you
okay, the correct answer is not there
yes,
in
the
that answer.
first and third options are printed
Um,
to be same in question number 3.
okay. So the present assignments, okay. So did you mail them?
Yeah, I did.
Did you reply?
One some Shayanton told that it has to be posted in the general group, so I have written there again, but till no response.
Oh,
Anyone can check that question. I mean, assignment 12, question number 3. Option A and C are printed to be same.
And
okay.
same problem will happen in 11 number. In that question number 3, option first is correct clearly.
Oh, you are talking about present assignment.
11th.
Shall we go to that? You are talking about present assignment, right?
Yeah, I'm talking about present 12, last assignment.
Okay. So I am. Wait a second, I'm just checking now only. Meanwhile, can you tell me which is the answer?
Answer to what?
First A, B, C, D now
A.
only. This is one. A. Okay, now let's see what is the answer. A. Okay, so answer is A. So I hope you can solve this type of problem in the exam. Let me share my screen for that. Mm, this is feasible now. Due 17. You're telling question number 11 and 3.
Question number 3.
Okay.
You see the option A and option C.
Oh, same
Uh,
only. And what answer you are getting? Is it matching with
no,
any
no,
of
no, no, no,
the?
no.
It's
It's,
not
it's
matching.
matching with probably both of them. I don't have the print sheet right now in front of me, but it's probably coming in
Okay,
both of them.
okay, okay.
One should be something else.
Okay, so wait. Okay, I am noting down. I will also tell them. And Ananda also you were telling about something.
Yes,
Question
ma'am.
number 3.
Last
Yeah.
week assignment.
That was assignment 11.
Uh,
Which question are you referring to, please?
Question third. Option A must be there, I think. It is clear.
Okay. It is a graph with the adjacency matrix A and the probability transition matrix. Which of the following is an A is symmetric? What you are telling? You are telling that answer should be A, not B.
Yes.
A is symmetric if P may not be symmetric if G is undirected. A and P not be symmetric if G is directed. A and P are symmetric if G is undirected, but A and B may not be symmetric if G is directed. If A, G is undirected, A will. Yeah. See, B is correct, but A is also correct.
I think they have given marks for A only. I thought B should be correct, but that
No,
was.
they have given mark for option B.
Did they?
Yeah, they should be given because answer is C, B only, right? So they are not checking manually. It is
But
computer based.
I think I have checked B, but I was not given marks for that. I'm missing something. Maybe I'll check once again.
See, A is symmetric for sure. P may not be symmetric if G is undirected. Yeah, this is correct only. Yeah, Ananta. Okay, so question number 3 of week 11, question number 3 of week 12. I will once check with them.
Has this solution been uploaded? This question, week 11 assignment?
No.
No, no solution is
Oh,
uploaded. I think, yeah, week 10 is uploaded.
week 11 is not
We,
uploaded yet, right?
yeah, yeah.
Only marks has been.
Answer is directly from the notes.
Yeah.
Sir has told by comparing
Yes, yes,
directed and
yes.
undirected graph.
Yeah,
In
yeah,
that
yeah,
P
yeah.
is not symmetric, not necessary. It's symmetric for undirected graph.
So, yeah, true, true. I also remember that. It is there in the notes. A and P are symmetric if A is. Okay, then. This question number 3. For others assignment, is it fine? So from here you can see the progress. Can anyone tell me like how many for how many weeks you have got full marks? Like what is the progress?
9 average. It's my average 9.
9 is average. Okay, very good. Because 25% will be this week assignments. 75 will be other thing.
Hmm.
Wait, I'll again share the screen. So okay, moving to the next question. So I have marked. I will check with them. I'll also mail from my end. Okay. So this is little different. In that first case, you're approximating with respect to
Frobenius.
Frobenius norm. Now you're approximating with respect to L2 norm. What will be the difference? Just think about it. So here, this question states it, if A is belongs to R 4 cross 4, such that this thing, and sigma is actually the ith singular value with ui and vi, the orthogonal column vectors, in SVD of A, find the nearest matrix to A in L2 norm with rank 2. And so answer is C. The nearest rank 2 approximation of A is denoted by as L2. This is this thing. Okay. Will it affect whether we are doing approximation with a Frobenius norm or L2
I
norm?
think it should not.
Yes. But logically, what was the logic? Like, how do we do that, the approximation? Do you remember in approximation, do we use any norm there? Yeah, I do agree that in every case we want the error to be minimum. But I think during approximation we didn't use that. So let's see the answer. What is the logic? Yeah, same only. See, it is same. And the vectors are also same. No, we have to
I
calculate.
calculate the singular values are different here.
But still the answer is same. Here A is given. I think the answer should be wrong then. The options should be wrong then. Or the singular values it should be same. 3 and 2. It should be 3 and 2.
7, 6.
See, everything is same. Then singular value should also be same. The formula is nothing. This one, this one. Okay. So just to clear you that whether it will be any norm in future, if it is L1 norm also, you do the same thing. Okay. Okay. So based on the given data in Q2, find the distance between A and its rank 2 in the Frobenius norm. Distance between A and the rank 2 approximation in the Frobenius norm. How to find the distance? Distance? Do we see any term distance?
Distance in the sense, take the norm, the difference, norm of the difference of the two matrices. Or maybe the residual part of the square of singular values.
Yeah, that can be the case. Or do we need to calculate the Frobenius norm for both matrices?
No, actually, the difference
A,
of them. I'll take the difference of the two matrices, the original one and the approximate one. Make the difference of that.
yeah, and calculate the Frobenius norm.
That should be the
Oh,
distance. I think so.
then we have to calculate A first, and then the approximation of A, which is A2, and then Frobenius norm. You're talking like this?
Or maybe if I don't exactly remember, there is a result that this Frobenius norm is actually the sum of the
Okay.
square of sum of the square of singular values. So if I take the first two singular values absorbed in the approximation, then the last two should remain. The square of
Yeah,
their
yeah, yeah.
sum should be the difference.
So as we can see from the formula
Yeah.
also, if you differentiate, if we subtract it, so these two singular values are left. Then we have to calculate the Frobenius norm for that. Frobenius norm is nothing but sum of the if the element is a11, a12, a21, a22. So what is the Frobenius norm? The Frobenius norm is a11
Sum of
square
the
plus
squares.
a12 square, a21 square plus a22 square.
Or you can say
Okay.
trace of A transpose A, square root of that. Trace of
Yeah,
A
yeah.
transpose A.
Yes. Okay. So this is one of the good question, not repeated one. Okay. Yeah. So in this case, we need to calculate L2 norm. Given the data in Q2, find the distance between A and its magnitude approximation in L2 norm. Okay, so this will not be Frobenius norm. In that case, it will be L2 norm. But you know, L2 norm of matrix is actually the same of Frobenius norm in matrix. I think so. See, though we are writing like this, 2, but the value will be same. If it is B, see, the value is B only. Because L2 norm of matrix is actually the Frobenius norm of matrix in matrix norm. Okay, so moving to next question.
Is that generally true? L2 norm of the matrix. I mean, L2 norm should be the largest singular value. Somehow here they are becoming equal.
No, no, no. What is L2 norm? L2 norm is also the uh, sum of square of the elements of a vector. Actually, it is defined for a vector. But if it is defined for a matrix, so what is the essence of that matrix? So if you are writing this as a A11, A12, A21, A22, this is A matrix. So you write like this, you make like this A11, A1, A21, this first column, then A22, A21, A22. And then first you convert this as a vector, this will be vector, then you find the L2 norm, then that is equals to a Frobenius norm. This was the main concept behind the Frobenius norm. Now, even if you don't convert this, so this will be nothing but A22 plus A21, A22. Okay, like this element, then this element. Okay, so anyway, these all are squared and summed, so it doesn't matter the order. So that's why L2 norm and Frobenius norm of a matrix is equal. Just the way of representation. See, the answer is also same. It should be same for all the matrices. Okay, question number 5. If A is this particular matrix 2 1 0 1 2 0 0 0 5, find the nearest rank to matrix such that the zeros are not perturbed. Oh, so zeros are not perturbed. So what to do if the zero is not perturbed? Means it should not change. Any guesses? Any idea? Any one of you? Ananta, you watched the lectures. Any idea?
No, ma'am.
Sir, you have idea?
Yeah, I think I did something. I don't
Pointers.
remember exactly what because I don't have the pen and paper right in front of me now. These zeros are to be kept in the same position, and the original matrix is symmetric. That we know something.
Matrix is symmetric, are you sure?
Given matrix,
No, it is. Yeah, some matrices are symmetric. L2 norm matrix with rank K sigma K plus 1.
yeah, that I was
Guru
having.
Sam is
I
telling
was
something.
having a confusion there as well. If blindly the L2 norm and Frobenius norm of a
Okay.
matrix should not be same. I mean, then there is what's the purpose of having two different names? If I remember correctly, L2 norm of a matrix is the largest singular value of something like it. It is the maximum of norm AX by norm X with norm X equals to 1.
Yes, yes,
That's the
yes,
spectral.
yes, yes,
Spectral norm
yes.
is called L2 norm, right?
Ah, yeah, yeah, yeah. So sorry for the confusion. So L2 norm is actually the largest singular value of the matrix.
And
True.
then why is it becoming equal to that? That may be something special here in this
No, no,
case.
no. Maybe why it is equal because for this particular case, maybe the singular value for that is 1. The matrix that you're following. L2 normal matrix is with rank K is a sigma K plus 1. He's also telling. Why not sigma K? It will be sigma K, right? Why sigma K plus 1?
Could you please explain a bit more, Mr. Guruswami? Why is it sigma k plus 1? Rank sigma k plus 1 means next singular value. K plus 1 is singular value, you win.
No, Guru Swami told this. I think should be largest sigma value, it will be uh, sigma K, right? It should be sigma K. Wait a second, I'm checking. But in intent also it is written L2 norm of a matrix is computed by treating the matrix as a vector. Okay. The Frobenius norm is computed by summing the squares of the elements. Basically, this L2 norm treats the matrix as single vector, while Frobenius norm consider the individual elements of the element. Show option D, ma'am. Okay, sure. Lucky
Among the
guy.
four, among the four answers, first three are rank 3 matrices and last one is rank 2 matrix. So that should be the answer.
In question 4, sigma 1 is equals to 1, sigma 2 is equals to 2, sigma 3 is equals to
The
1.
Hankel matrix, 1 plus 1 by 2.
Acha, 1 plus 1 by 2.
Yeah, like first column plus second by 2.
Oh, okay, okay. So we need to keep the zeros as not perturbed. We need to calculate the Hank matrix. First column plus second column. Oh, okay, okay. I remember. Yeah, yeah, yeah. That was a formula for B, right? Was
Only the last one seems to be Hankel.
2 plus 2, 1, 1, 2, 0, 0, 5, 0, 0, 5. So this is this is 2 plus 1, this is 1 by 2. Sorry, 3 by 2, this is 1.5. This is zero point 0.5. This is 1.5. This is 1. No, this is 1, yeah. 0, 0, 5. And that will be same, right? So this is
Both will be 1.5.
uh wait a second. So slow. That was B dash. I remember that B dash. Lakana is telling only D is rank 2. Only D is rank 2.
Other three are of
All
rank 3,
others,
madam.
others are rank 3. So, okay. But okay, like it is asking rank 2 meters. That is fine. But what is the logic? Like how to keep that the zeros as not perturbed? That one observation is very correct. But I think other Guru Swami is telling about an other example. अरे यार ये खुल जाए.
Can you please place the question once again? You are on the screen.
We saw somewhere we saw right sum plus divide by 2. That should be the logic.
That's a Hankel matrix.
Hanged, right?
This is even particular. It is
Anchored.
not. It is just symmetric. So you have to put just sum and divide it by 2 in the two corners.
Yeah, that is what I saw.
Yeah. Hankel would have been more general.
No, I was seeing that thing.
No, in the video, professor have explained that clearly. That it's symmetric, then you have to put it like that. You take the average of that because to maintain symmetry.
Okay.
It's kind of lift and project. There.
Okay.
There you see.
So first of all, let's go to question number 5. He's telling something. Question 4, sigma 1 is equals to 1. What you have written? Sigma 1 is equals to 1. Sigma 2, what you have written? Guru Swami, what you have written? Okay. After calculating, you might have got sigma 1 as in this question. Sigma 1 is equals to 1. Sigma 2 is equals to 2. Sigma 3 is equals to 1. Okay, so that's why you're telling that for L2 norm, the sigma k plus 1 will be the value, will be the answer. Okay, for any matrices, so if matrix A is given, so if you have to calculate if you want to calculate the L2 norm of a matrix, you remember. So my apology is that L2 norm is not same as Frobenius norm. I thought like a vector kind of thing. But yeah, if a matrix A is given with a rank K, if A is given with a rank K, so L2 norm of A will be sigma K plus 1. So in this particular thing, if you calculate it as Guru Swami has done, so sigma K plus 1 is coming, which is sigma 3 is 1. Okay.
Yeah, so that means the first two has been taken in the approximation. Whatever the remaining part is there, you calculate the largest singular value of that will be the first one. That the largest one there is k plus 1. It's exactly. The remaining part, the largest one is sigma k plus 1, and that's how It is the largest singular value of that particular part which is left.
Yes, yes, yes. And yeah, sigma 1 is actually 3, sigma 2 is 2, and sigma 3 is 1 in this particular. Suppose if this is B matrix, so B matrix have these things. Okay, so since we just have to sum it and divide by 2, so 3, 3 by 2, 3 by 2, and this will be summed. So yeah, answer is written like this. In order to keep all the zeros unperturbed, we need to either 0 out of 5 in A or reduce the rank of the upper left block matrix. Okay, we can reduce the rank of this one. Since the smallest singular value of the upper left block is less than 5, therefore smallest chain that we can brought to A by reducing the rank of a upper left block matrix. Thus we need to find U1, U1 transpose and sigma 1, U1 transpose 2, U2 transpose the upper left block matrix and replace it by sigma 1, U1 transpose. Okay, so if what the concept is saying, if we don't want to perturb this, so let us keep it this, and if this is a matrix left, this is 2 1 1 2. So uh you need to approximate if this is a rank 2 matrix. So you need to approximate with the rank 1. So sigma 1 u1 v1 transpose. You need to replace this particular matrix with this one. So the sigma 1 u1 v1 transpose will be 0.15, 0.15, 0.15, 0.15, because I think sigma 1 values will be there 0, 0, 5, 0, 0. So this is the analogy. But yeah, your thing is also, observation is also correct. That all these things are rank 3 and this is rank 2. So yeah, but in order to do in future also, if it is asked in the future, how will you do? You have to keep this zeros as it is, and whatever the left part is, you can approximate that. Okay, so in that case, that will be the way. That can be the way. Okay, so you need to know how to approach the problem because same set of problems will be repeated. Now, find the distance in Frobenius norm to the nearest rank to approximation. Again, how will you define the distance? Using this particular formula, sigma 3. So what will the distance in this case? Yeah, what will the distance in this case? Distance will be sigma 2 u2 v1 transpose, u2 transpose. Okay, this will be the distance. How many of you agree this will be the distance? Where sigma 2 will u2 v2 will be corresponding to this particular matrix 2 1 1 2. How many of you agree? Or is there any other approach?
What if I straight away find out the distance and the Frobenius norm of that? The original matrix is known.
Yeah, distance. See, the simple thing is you can find that you can subtract this matrix with this matrix and find the distance. That's fine. But uh, what will be the exactly it is equal to? It will be equal to this one because this is written only in terms of using sigma 1 u1 v1 transpose, and this A matrix is nothing but sum of sigma 1 u1 v1 transpose plus sigma 2 u2 v2 transpose. And if we subtract it, this with this, it will be sigma 2 u2 v2 transpose.
So sigma 2 will be answer.
So you simply subtract the lower rank matrix and find the Frobenius norm. That is fine. Other way. Okay. Let us find this equation. So let us solve this question. If A is a 4 cross 4 symmetric matrix having the eigenvalues 3, 2, 1, 0, corresponding eigenvectors are this, find A. How will we do? It is square of sigma 2, no sigma 2. Why? Why it will be square? Because you always write A as sigma 1 U1 V1 transpose for sigma 2 U2 V2 transpose. Now we are telling that we are approximating with respect to sigma 1 U1 V1 transpose. Let's keep 0, 0, 5 as a single thing. Okay. Now if you subtract it, it will be nothing but sigma 2 U2 V2 transpose only, no square. Similarly, we did before also. Here, okay. Frobenius norm. Yeah, norm will be square. Okay. So we need to, this is a matrix. So sorry. This is a matrix, and in order to calculate the Frobenius norm, it will be sigma 2 square. Okay. Because we need to calculate the Frobenius norm of this. Similarly, here also we did similar sort. Where is that? Yeah, we need to calculate Frobenius norm of this particular matrix. Okay. How to solve this question number? Which was the question? Yeah, how to solve this question? There are 4 cross 4 symmetric matrices with the eigenvalues this one. Find A using the similar sigma 1. B lambda B.
All the eigenvalues are distinct, so you can have this spectral resolution. The orthonormal matrix there, V formed by these
Yeah.
columns, and its transpose will be its inverse. So plug in from both the sides, and that will give you an answer.
Yes. This is transpose also. So V will be nothing but 1 0 0 1 1 0 0 minus 1 0 1 1 0 0 1 minus 1 0, and this lambda
With the
is
1 by root 2 outside.
yeah. It can be 1 0. This is the
No,
identity matrix,
1 by
right?
root 2 will be with V, with the matrix.
Acha, okay. I didn't saw that. Okay, eigenvalues are this one. 3 2 1 0 0 0 0 0 0 0 0 0 0 0 0 0 0. Okay, so you need to calculate using this particular formula. Okay, question number 8. Consider the data given in Q7. Question number 7. Find the nearest rank 1 approximation to A. So what was that? Sigma 1 U1 V1 transpose, or lambda 1 U1 V1 transpose, or say lambda 1 U1 transpose, because this is symmetric matrix. So let us solve this. Lambda 1 is nothing but 3. U1 and U1 transpose. Okay, 1 by root 2, if we keep it up, 1 by 2. This is 1 0 0 1. 1 0 0 1. 1 0 0 1. This is 1.5. This is 1 0 0 0 1. Sorry.
First option.
0 0 0 0 0 0 0 0 1 0 0 0 1. So answer should be A.
Yes.
Okay. Find the Frobenius norm distance. Oh, same sort of question is there. How do we calculate this? Find the this will be Frobenius norm of sigma 3 U3 transpose plus sigma 4 U4, sigma 2 from sigma 2 itself, U2 transpose plus sigma 3 U3 transpose plus sigma 4 U4 transpose. Frobenius norm. This will be the distance. Or
Just sum of the square of the singular values and the square root of values.
yeah, it will be sum of the square of singular values. Hmm. So I hope this type of problem you can solve. Frobenius norm, distance. Nice. Similar set of questions is there. Now L2 norm distance from the nearest norm. So it will be sigma. Guruswami, what will be the answer for this? L2 norm distance from the nearest rank 1 matrix. Sigma 2. Sigma k plus 1. This is 2. Okay. Sigma k plus 1 means sigma rank 1 is k plus 1 sigma 2. Sigma 2 is 2. Okay. So there are some concepts, but the concept once you understand, everything is repeated. So, okay. Now tell me what topic you would like to discuss in the live session. The last live session, which is scheduled on 17th of April from 6 to 7. See, week 12 we have discussed it properly. I think we don't need to. The same sort of questions will be repeated. Uh, Among others, which was the week that seems to be more difficult. I will also spend time studying and then I will discuss. It will be some sort of things that I also don't know. But yeah, by discussing among ourselves, it will be easy. Yeah, yeah, Lakshmi.
Just this previous question, to find the closest rank one vector, sorry, matrix to A. Just before this, I think. Yes, the previous one. Question was, no, before this also, I think. Yeah, question number 8.
Yeah.
How did you do this? What was the formula applied? Nearest, how do you find the
Yeah.
rank one matrix to a given matrix?
Yeah. So to find the approximation, for if the rank 1 is given, if the rank k is asked, so our formula is sigma 1 u1 rank k will be sigma 1 u1 v1 transpose plus sigma 2 u2 v2 transpose plus sigma 3 v u3 u3 transpose, so on up to sigma k. Okay, this is the approximation formula that we have seen in the class. Okay, now UK VK transpose. Okay, so sorry, this is VV. Okay, now since this is a symmetric matrices, this is a symmetric matrix. So as we know, symmetric matrix U is actually this, small u is actually small v and capital U is equals capital V, because symmetric matrix can be written in terms of singular value decomposition. Sorry, eigenvalue decomposition. And eigenvalue decomposition, it is equal to singular value decomposition in symmetric matrices. So that's why this was first I saw sigma 1 u1 v1 transpose, which is equals to lambda 1 u1 v1 transpose, where u1 v1 and u1 are same, so it is equals to lambda 1 u1 u1 transpose, and then we have solved.
What is sigma u1 v here?
Yeah, sigma is the eigenvalue, or the sigma values. Sigma value actually sigma is actually sigma value is the singular value decomposition, where u1 is the matrix. Sorry, the vector in U matrix that was there in the singular value decomposition. If you remember the singular value decomposition, states that any rectangular matrix can be written in terms of, it is not square, it is rectangular, can be written in terms of U sigma V transpose. Okay, where U is actually the vectors of U are A transpose A, no, A transpose, A transpose, and vectors of eigenvectors, sorry, eigenvectors. This is eigenvectors, okay? This is eigenvectors of A transpose A. Okay,
Okay.
yeah. So this is a formula, approximation formula you need to remember. And using approximation only, we have found Frobenius distance and everything. Yeah.
So like, so what is sigma 1, u1, sigma 2, u2, sigma 3? Like, how do you get those components?
Okay. So basically, this that we wrote there, U sigma V transpose, can be written as, yeah. So sigma is actually sigma 1 0 0, sigma 2 0 to sigma n. This is the diagonal
Okay.
matrix, okay? And this is also equals to this particular can be written in terms of individual u. You remember this u is u1, u2 to un. These are the columns.
Columns. Okay.
V is v1 to vn.
Right.
And this particular thing can also be written as sigma 1 u1 v1 transpose plus sigma 2 u2 v2 transpose.
Right.
As we know, sigma 1 values are decreasing in number. Sigma 1, sigma 2, sigma n. Okay, so that's why in order to get the particular rank meters, you all you consider only kth sigma value,
So the
because we are
small sigma 1, sigma
we
2, are they square root of eigenvalues?
yeah, that's square root of the eigenvalues. So any suggestion on the live session, last live session that I'll note down, then I'll prepare, because please comment in the chat box. As all of you are attending week 12, so I hope all of you will appear for the exam. So don't worry that you don't know any concept or you forget anything. Try to revise it. And how to revise, I'm telling. Take the notes and then keep the video in 2x and then try to watch. Whatever concept that you're forgetting, please watch the lecture. Because I also forget the last optimization. Then I will watch the lecture and then I'll remember that this is the way that we should do. And once we know that this is the proper way that we should follow, then you will be able to solve the problem as well. Preferred it on graph. Graph? Okay. Means week 10. Okay. Anyone else? Week 11. Yeah. If possible, previous year question on a model game. Yeah. So what happens? We are not. I checked with the NPTEL team. They are not giving me previous to previous year problems so that I could say give it to you or solve in the class. I am only accessible to previous year questions. Okay, so I will take week 11. And do you have any problem or confusion in uh, this sensitivity analysis? Because that is also one of the main topic. Okay, so let's meet on 17th of April, 3 days only. Just for your revision, please do attend. Yeah, please do attend. Even if you are very confident that you will score good, so yeah, but in order to revise some of the concepts, just do it. Okay. So thank you for joining. Yeah, thank you.
Last week's assignment, can you solve the questions based on that Markov chain?
Yeah, yeah, we solved also in the class properly. Week 11 questions, I think. We solved every question in the class. Actually, recording is also uploaded. You can see that also. Like the the last half an hour, you don't have to watch all the, but last half an hour we saw. See, this is my marked things. Wait, I'll post the link here only. Give me a second.
middle class